The world that we perceive in everyday life is really a classical world. Because of the magnitude of our size and our ability to perceive things, we see objects as moving more or less according to Newtonian physics. However, about 100 years ago, we began to discover that molecules were not quite the same. In fact, they may not follow that picture. So I want to distinguish between what is inherently a classical picture, a classical physics picture of the world, which is the one we're used to, and the molecules picture of the world, which is a quantum physics picture of the world. So what is the difference between these two? Why is there some distinction that we need to worry about? Well, in the quantum world, it turns out that matter has something peculiar called a wave-particle duality. Now, this isn't going to have much bearing on large systems per se, but it does affect the energies that are allowed of these molecules. So this is why we're bringing this up now. And in fact, I'm going to say that a lot of the material that I'm going to talk about here and maybe in the next video or two is really stuff that you will learn in the other half of physical chemistry. And it's not that I'm trying to preempt that other half, but there's a few little details that we need to know so that we can do our job right in this course. All right, so molecules, it turns out, are particles, but they also have some sort of wave-like character. So exactly what does that mean? Well, back in the 1920s, a PhD student named Louis de Broglie hypothesized that one could assign a wavelength to a particle, and it was related to the momentum of the particle. So the momentum is in the denominator, and this thing h here is Planck's constant. And it's a good idea to know that Planck's constant is roughly 6.63 times 10 to the minus 34 joule times seconds. Okay, so it's a really tiny constant. And look, it's in the numerator, so that it means that anything that has an appreciable momentum is going to have a really tiny wavelength. And this is important because what it means for us in terms of our experience is that large bodies or large objects, and I'm going to say that these are heavy objects, so they have an appreciable mass that's here in the denominator. These are going to have really infinitesimal wavelengths. Okay, well, something that has a really small wavelength doesn't look much like a wave. It looks more like a particle. But what if we have something that's small? What if we have a small, very light object? So I'll say very light. And this could be something like an electron or even a hydrogen atom. In this case, what we find is that they have very appreciable wavelengths, and in fact they have detectable wavelengths. Detectable. So we now need to take account of the fact that they are waves. Now I should probably stop for a second and describe, if you haven't had this in physics before, that the wavelength, if we have a wave, it's something that's oscillating up and down, and the wavelength is basically the distance between two consecutive crests. So it's telling us something about the physical aspects of the wave that these particles make up. All right, now what does this have to do with these molecules? Now, it turns out that the molecules exhibit this wave-like behavior in the way that they form energy levels. And what I mean by this is that we're used to an object being able to have any energy we want. So for example, if I throw a baseball, I can throw it at, well, I probably can't throw it at 90 miles an hour, but let's say I could throw it at 90 miles an hour, or I could throw it at 90.1 miles per hour, or I could throw it at 90.0000001 miles per hour. There's nothing that limits the speed at which I can throw that baseball. But quantum mechanics would say something different. It would say, in fact, there are certain discrete levels at which I can throw a baseball. The problem is that the difference between them is so small I would never be able to detect it. But this isn't true for very small objects like electrons. All right, so what we're faced with is this business that we have to figure out for small molecules. What are those energy levels, and are they spaced widely enough that we can actually detect them? Now I'm going to start by talking about translational motion. We talked a little bit about that with degrees of freedom, so we know that each molecule has 3 translational degrees of freedom. All right, so the way I can manifest the quantum mechanics of this would be if I were to draw a box, and I'm going to make it a 3-dimensional box. So let's draw our box something like this. So this is the front face of the box, and it goes back. Here's the side face of the box, and then I'm going to make little dash lines here to indicate that it's a 3-dimensional box. Now I'm going to label the dimensions of this box. I'm going to make this be the x dimension, so it has a length of Lx. I'll make this be the y dimension, so it has length of Ly, and this be the z dimension, so it has dimension of Lz. Now, the reason I'm specifying this box is this is going to be the volume in which a gaseous particle is moving around. And it turns out because it is a quantum mechanical object and this box prevents it from going outside the box, that means its wavelengths have to fit in the box. So it's going to have some integer number of wavelengths that span the various dimensions of this box. That's what makes it quantum mechanical. But you'll, I hope, realize that I can't have an integral number of wavelengths for every possible wavelength. Okay, the number of wavelengths is going to be fixed by the size of the box. Now, we're not going to work through the quantum mechanics here, but I will mention that the energy levels of this system, quantum mechanically, the translational energy levels would look something like this. So I'm going to write E trans is equal to h squared. This is the same h, this Planck's constant, over 8 times the mass of the particle, and it's going to be equal to an integer squared over the length in x squared, plus another integer squared over the length in y squared, plus a third integer squared over the length in z squared. And this is what gives us the energy levels that are allowed by the fact that this particle has to be a wave and it has to have a set number of wavelengths that fit inside this box, which is basically outlined by these 3 dimensions. Now I want to make this a little bit simpler just so we can compare some magnitudes. I want to say that Lx equals Ly equals Lz, and it's just equal to some generic length L. So we've got a cubic box now. So that means that our energies are going to be given by h squared over 8m L squared. And now I can just put these 3 squared integers in parentheses by themselves. So what are these 3 integers? Where did they come from? These are what we call quantum numbers. And these quantum numbers are the ones that basically dictate exactly what energy we're talking about. So you can see that the energy here is in fact a function of these 3 energy levels, or sorry, these 3 quantum numbers, as well as a function of the dimensions of the box and the mass of the particles. But these quantum numbers now can take on any value. So nx, ny, nz can take on any value, 0, 1, 2, 3, and so forth. And because it can take on any of those values, that means I have a whole bunch of energy levels in this box. Okay, now in the case of translation, and this is one reason why I hesitate to bring this in first, if the box isn't very small, that is to say if the box, say, is 1 centimeter cubed, okay, which may seem like a small box to you, but it's a huge box to a molecule. If I have a box that's about 1 centimeter cubed, then this set of numbers out here is going to be something on the order of 10 to the minus 38 joules. So in other words, this is really not much energy. I think we can all agree that 10 to the minus 38 is a pretty small number. And I'd have to have pretty big quantum numbers here to even get up to multiply by this to make this something that I could measure in a laboratory. So as a result, what we find is that for most objects, even molecules, the translational levels are so close together that they effectively make the particle behave as though it is classical. So translational energy levels are extremely close together. So it turns out your intuition wasn't so bad after all. A molecule moving around really does look quite a bit like a classical object, but we do want to take into account the fact that it has only certain discrete energy levels. And we'll see where this comes in as we explore this notion a little bit further for the other degrees of freedom that we've already talked about.